Hi, welcome back. Today we're going to talk about critical numbers and why they're very important for us in calculus. Now, a critical number most of you guys have seen before. If you think of a parabola in calculus, a critical number for us in calculus is where something is changing. And if we look in terms of a parabola, the easiest thing to tell of what's changing is the slope. So where does the slope change? At the vertex. And at the vertex, the slope is going from a positive slope, in this case, a negative slope to a positive slope. So where does that change occur? Down here. And that is called a critical number. Now, critical numbers occur in two ways in calculus. In calculus, to get a critical number, and I'm going to be at a CN, a critical number is one, where does the derivative equal 0? Or where does the derivative not exist? So it can occur at vertical tangents and such like that. This is our horizontal tangent, which is very obvious from the vertex. So if we want to find a critical number of a problem, we're going to need a derivative. So if we take a look at a quick example here, let's say f of x equals, let's say, 5x cubed plus 5x squared plus 9. And I want to find the critical numbers. Well, my first step is to just take the derivative. We get 15x squared plus 10x. Now remember, the 9 goes away. So I have two ways I can get a critical number. One, where does the derivative equal 0? Or two, where does the derivative not exist? Now this one's pretty obvious. There's nowhere where it's not going to exist because there's nowhere where x can't exist. So that's not going to exist there, nowhere. But let's take a look at where it's 0. I set that equal to 0. I can factor out a 5 and an x. And that's going to give me 3x plus 2 equals 0. And I just solve it. X equals 0, x equals negative 2/3. And those are our critical numbers. Now, why are these so important? Remember, this is telling me where the slope changes in this case. For the most part, there's a little more to it. We'll get to that later on. So what it's telling me, something at 0 and at negative 2/3, something is happening. Well, we know from earlier, from pre-cal, that this is an odd positive function. So they start negative and they end positive. So what that's telling me, somewhere over here, the slope has to change on this point. So it's negative slope, starts down, okay, going up, and it's going to look something like here's 0, and it's going to go back up again. Okay, so that's kind of like what it helps us to graph the original function. At these points right here, we know the slope will be 0. Now, later on, we're going to use these to determine how can we find a relative max or min. And we're going to do that in another video in just a second here. But I want to take a look at another example, one where we have one that does not exist. So let's take a look at this weird looking function. F of x equals 8x to the 5/4 minus 8x to the 1/4. I want to find the critical numbers. So I take the derivative. That's easy. I get 10x to the 1/4 minus, be careful, 2x to the negative 3/4. So there's my derivative. We don't like a negative exponent, so we will rewrite it. 10x to the 1/4 minus 2 over x to the 3/4. Now we want to write this as a single fraction. And I do that. This my common denominator, x to the 3/4. And if I multiply here, that becomes just 10x minus 2. There's my derivative. But we haven't done the critical numbers yet. Remember, one critical number, where is the graph 0? Where is the slope of the graph? Non-existent. Well, where it's 0, it's easy. That's just the top. So I set my top equal to 0. I get x equals 1/5. Where does it not equal to 0? Where it does not exist, that's the bottom. That's my vertical tangent. So I said, look at the bottom. X to the 3/4 equals 0, and I get x equals 0. So it's undefined here. But these are both critical numbers. Something's happening there in both of them. In this case right here, it's most likely a vertical tangent. Okay? All right, and we'll do more tomorrow.